Atomic weaponry has a very dramatic and controversial history in the human age. It was first developed in the early 1940s, and as the Second World War raged on, in an effort to develop the technology before the Nazis were able to. It wasn't ever done before, but only theorized that it could potentially provide a swift and decisive victory to whichever power had developed it first. Luckily, we had Albert Einstein write a letter to President Roosevelt on August 2nd of 1939, about a month after World War II officially began, expressing his concerns that this technology was possible and of utmost importance to investigate. Not even 5 years later would the United States use it to aid in the surrender of the Japanese Empire. This would be the first and, so far, the last time a nuclear weapon would be used in the theater of war. This picture illustrates the destructive power of the bomb called Little Boy, with a before and after picture of Hiroshima. These were the first generation nuclear bombs that worked via nuclear fission. Second generation hydrogen bombs, or thermonuclear bombs, use a bit of different method and worked by nuclear fusion. Nuclear fusion delivers a much greater amount of energy released per material used and is therefore much more destructive. Nuclear fission works by subjecting an unstable atom to an atom force such as one provided by a fast-moving neutron. Uranium has a particular unstable isotope, U-235, that was often used in the beginning of an atomic weapon experimentation. This isotope is particularly subject to nuclear fission reactions once bombarded with neutrons. Fission works by splitting up an unstable, heavy nucleus into more stable nuclear products. In this example shown, we have an atom of uranium-235 being struck by a neutron to create krypton-92, barium-141, and an extra 3 neutrons along with an enormous amount of energy. The creation of the extra 3 neutrons is what causes this reaction to be referred to as a chain reaction or a runaway reaction. The 3 neutrons produced will go on to fission any unstable uranium-235 nuclei nearby and continue the process. Law of conservation of energy states that the energy released from the nuclear reaction must be equivalent to the difference between the energy in the product nuclei and the neutrons and the starting uranium-235, which turns out to be a large amount of energy. Pictured above is the bomb called Fat Man, an implosion-type plutonium-core nuclear weapon with a weight of 10,300 pounds. Below it is Little Boy, a gun-type uranium core fission weapon with a weight of 9,700 pounds. Both of these weapons work by nuclear fission, but the fissionable material is what differs between the two. Uranium and plutonium are both elements that contain a lot of neutrons and are very heavy and therefore unstable. Nuclear fission is the other type of nuclear process that can occur and involves the fusion of 2 lighter nuclei to create a heavy nucleus. This is the type of nuclear process that the sun uses to produce its abundant and long-lasting energy, and is the same process that the universe has used over time as stars live and die to generate every nucleus of every element that is found in nature. In terms of how it can help us here on Earth, naturally and unfortunately, its use was first discovered in an attempt to create weapons because of the American government normally decides to bankroll weaponry development before moving on researching civilian applications. Since then, scientists have become interested in developing nuclear fusion in order to create energy as we move away from fossil fuels and other climate change contributors. Nuclear fission has been a proven way to create energy, but there are still drawbacks in it that creates toxic waste that must be especially stored, and catastrophic failures at the hands of human error can occur as seen in Chernobyl and 3 Mile Island. This is why nuclear fusion may theoretically become a more desirable method of energy production, as it won't produce much radioactive atom waste and will be a much cleaner source of energy. In this diagram, we show an atom of deuterium and an atom of tritium fusing together to yield a helium atom, a neutron, and energy. Deuterium is an isotope of hydrogen that contains an extra neutron, while tritium is also an isotope of hydrogen that contains extra 2 neutrons. The extra neutrons are necessary in order to form a stable helium atom once fusion takes place. Helium is an inert noble gas and much more desirable as a byproduct in nuclear reaction as opposed to the radioactive byproducts from fission and of uranium and plutonium. At its current state, fusion research has come a long way, but has still yet to become cost effective. And since money drives most of how civilians operate, it doesn't make sense to produce energy through fusion if it will end up costing us more money than companies will make on the energy sold. Once that threshold is crossed, I'm sure it will be, nuclear fusion may be a mainstay in how humans generate power.